Hey there, and welcome to The Explainer. Today, we are cracking open the Cambridge Additional Mathematics 0606 syllabus. Specifically, we're zeroing in on one of the absolute highest stakes, multi-stage topics you're going to face, finding the maximum or minimum value of a quadratic function. Let's dive right in and figure out how to completely automate this process using either completing the square or differentiation. Now, the sheer weight this specific topic carries, it's honestly kind of mind-blowing. Look at this quote from a senior examiner. This topic appears in every examination series. Seriously, every single one. You literally cannot hide from it. And, well, you shouldn't want to. Whether you're asked to complete the square or use differentiation, this is just one of those ubiquitous problem types. Nailing this doesn't just grab you marks for one question, it lays a massive foundation for the entire paper. We're going to transform what usually feels like this chaotic, messy calculation into a highly automated, super efficient pattern in your brain. So here's our roadmap for today. 1. Core principles of quadratics. 2. Executing technical methodology. 3. Solving and evaluating effectively. And finally, 4. Crucial examiner insights. All right, let's jump right into Section 1, Core Principles of Quadratics and the Cognitive Domains. Look, Cambridge isn't just checking to see if you've memorized a formula. They're actually targeting 3 completely distinct cognitive domains here. First up, knowledge and understanding. Like, do you actually know the rules of differentiation or the raw algebra behind completing the square? Second is application to unfamiliar contexts. Can you extract the mathematical model from some weird word problem about, say, a bridge or a projectile? And third, and this is absolutely crucial, analysis and structured reasoning. This is where the real magic happens. It demands a totally connected, conceptual understanding where you mathematically prove exactly why a specific point is a maximum or a minimum. So the big takeaway here is this: prioritize analytical depth over superficial breadth. Think about 2 totally different students, right? Student A just word vomits raw math facts onto the page, totally rushing the algebra, skipping explanations, and completely ignoring the command words. Then you have student B. They take a breath, analyze the quadratic function, and lay out totally logical, evidence-based reasoning for every single step. Examiners are literally hunting for student B. They want to see your analytical depth, not just your speed. Which perfectly tees up Section 2, Executing Technical Methodology. This is the procedural framework. If you want to dodge cognitive overload during these huge, multi-stage questions, you've got to automate your process. It's like programming your brain. You just follow these 5 steps every single time. Step 1, deconstruct the question. Like, what are the actual command words here? Step 2, extract the relevant data. Step 3, select your analytical framework. Are you completing the square to find that vertex, or taking the first derivative, setting it to 0, and testing its nature with the second derivative? Make a firm choice. Step 4, execute with super clear notation. And Step 5, present it all with correct terminology. By chunking the problem like this, you basically delete panic from the equation altogether. And really, this is exactly why we use that specific 5-step process, the method mark strategy. In Cambridge 0606, the journey is honestly just as important as the destination. Examiners actually award credit just for your step-by-step mathematical process. If you explicitly show your chosen analytical framework, say clearly writing down that you're setting dy dx to 0, you lock in those method marks. Even if you make some silly arithmetic mistake at the very end, you just got to show the examiner you're thinking. But, and this is a big but, to actually secure those method marks, your data interpretation and presentation have to follow some incredibly strict conventions. The examiners have a rubric, and you've got to satisfy it. Use proper headings. Use the correct terminology. Please don't just say it goes up. Use actual terms like positive gradient or maximum turning point. Use the right formats, clear annotations. Basically, treat your exam paper like it's a professional mathematical report. Moving right along to Section 3, Solving and Evaluating Effectively. So we call this the deconstruct, solve, evaluate loop. Honestly, it's the ultimate problem-solving sequence. You've identified the info, broken it into steps, and solved it. But check out Step 4 on the screen. Check for reasonableness. Think about it. Did you just calculate that a thrown ball reaches a maximum height of -5 meters? Because if you did, something is definitely wrong. And finally, Step 5, make justified recommendations based purely on your math. And as part of that reality check, you absolutely must identify limitations, assumptions, and how they actually affect your conclusions. High-tier evaluation means stepping back and asking if that mathematical minimum or maximum actually fits the real-world context they gave you. Like, if your quadratic model's a physical area, your dimensions obviously can't be negative, right? Acknowledging those constraints explicitly is a massive flex. It shows the examiner you have top-tier analytical skills. All right, Section 4, Crucial Examiner Insights. This is the reality check. We are diving straight into the principal examiner reports to see exactly where students are bleeding marks. There are 3 major mistakes that come up over and over. Mistake number 1, vague answers. Students just slap in numbers on a page, but the examiner's expectation, they want specific, detailed, methodological steps. Mistake 2, poor formatting. The expectation here is total adherence to strict mathematical conventions, clear notation like we talked about earlier. And mistake 3, ignoring context. You have to tie your final answer back to the actual scenario. If you can safeguard yourself against these 3 specific mistakes, your mark potential is going to skyrocket. I really want to pause on this because it's an explicit alert direct from the examiners. Quote, candidates consistently confuse key terminology. Always define terms before using them in extended responses. End quote. Whether you're explaining the vertex form of a quadratic or you're using comparative connectives to explain why a second derivative being less than 0 proves its maximum, your language has to be surgical. Precision in your language totally reflects precision in your thinking. So, how do you actually execute all of this flawlessly when the exam clock is ticking? It really helps to synthesize all these procedural steps into a mental model. Let's call it the visual story method. Basically, it's a memory hack that encodes the complex sequence of, say, differentiation or completing the square into a narrative you won't forget. Imagine the x-squared term is the foundation of a house. Before you can even think about building the roof, which is your vertex, you have to factor out that a coefficient to literally clear the plot of land. By turning these dry, procedural steps into a vivid mental movie, you're automating your efficiency. You're basically becoming a mathematical machine, just smoothly shifting through the gears of the problem. So, as we wrap up this explainer, I want to leave you with one final thought. Have you optimized your own procedural framework to secure every single available method mark on your next quadratic analysis? Seriously, don't just practice the math anymore. Practice the system. Take these core principles, lock in the technical methodology, evaluate your final answers, and do not forget those examiner warnings. Run your next past paper through this exact blueprint, and you'll see the difference for yourself. Thanks so much for hanging out with me on this explainer, and keep learning efficiently.